Hey there guys, in Unit 1, Note C, we're going to talk about matter. This should be mostly reviewed from 8th grade, so I'll try to keep it short and sweet. Matter is anything that takes up space and has particles. It's the stuff. So if it has mass and it has volume, then it is matter. The only other type of material, the only other type of thing out there is energy. Typically things fall into either matter or energy, so in chemistry we study matter. In order to be classified as matter, it must have mass and volume. Here we have a classification map of matter. Two main categories of matter are pure substances or mixtures, but you can also see that each of those is divided up into two smaller categories as well. Pure substances could be elements or compounds, whereas mixtures could be homogeneous or heterogeneous. First, let's look at the two big overhead categories. It can either be a pure substance or a mixture. If it's a pure substance, it's going to be one type of material. The entire substance would have the same properties. For example, water. Every droplet of water has the same exact properties, the same exact melting point. You could say the same for a bundle of oxygen gas. Mixtures, on the other hand, are going to be combined together, two or more substances mixed together. So water mixed with salt, like a salty water, you could separate the salt and the water. If you evaporate out the water, you'd be left with the salt. Salt is gritty, water is, liquidy. So very different chemical properties. So if you take two pure substances and you mix them together, we would call that a mixture. Now let's talk about the subcategories under pure substance. We could have elements or compounds. So elements would be the most pure substance. Literally a single atom could be called an element. We have a periodic table of elements. So if you're talking about the individual atoms, we're talking about elements. But you might know that atoms sometimes combine together. We mentioned water earlier. If I combined the hydrogen and the oxygen, yes, there are certain ratios that this happens in, but anytime that you combine two different atoms together, you're going to get a molecule. So we call those molecules a compound. To kind of put this in more uniform terms, elements are made of atoms. The atoms are a building block of the elements, whereas compounds are made of molecules. So the molecule would be the building block of the compound. You're talking about the substance as a whole, you'd call it an element or compound. If you're talking about the individual particle, you can call it a molecule or an atom. Before we move on to look at mixtures, I want to point out that the most commonly mixed up substances are compounds with homogeneous mixtures. Notice while we're looking at the compound that it actually comes together to form a chemical formula. The H2O, the hydrogen is bonded to the oxygen. That combines together with a chemical bond to form a molecule. Something very different when you look at a homogeneous mixture. Now let's look at mixtures. So the two types of mixtures are homogeneous and heterogeneous. Homo actually means the same, and geneous means composition. So homogeneous would have the same composition, meaning it has identical properties throughout. Example of this would be like a smoothie or some salt water, whipped cream. If you go and get a strawberry banana smoothie, you couldn't halfway through decide to take the banana out of it. It's all mixed through, uniformly mixed through, identical properties throughout. No matter where you stick your straw, the taste is the same if you have a homogeneous solution. If we're looking at heterogeneous mixtures, hetero means different, and geneous again means composition. So this will have different composition, very different properties. So things like granite or potpourri, maybe a more relatable example would be like Lucky Charms. You could pick out the marshmallows, or you could save them for last, and that's because they have very different properties that make them very easy to pick apart. And again, at the end here, I want to point out that the most common mix-up is between homogeneous mixtures and compounds. Notice that a smoothie does not combine to form a new compound. You can't write a chemical formula for a smoothie. A smoothie is made up of separate things. Strawberries and bananas have different molecular structures. They're not combining to form a new molecule. Compounds combined on a chemical level. Mixtures do not. Next, we're going to look at two very important laws. And they're very similar, but one has to do with matter and one has to do with energy. With the law of conservation of matter, sometimes referred to as the law of conservation of mass, It says that matter cannot be created or destroyed. The particles are preserved. The law of conservation of energy says that energy cannot be created or destroyed. But actually, in both of these circumstances, you can have a transformation. Matter could be turned into other matters, such as in a chemical reaction. Energy could be turned into a different form of energy, like potential energy turning into kinetic energy. You can have a transformation, but matter simply does not appear. There is no actual bunny coming out of the hat or an actual lady disappearing. Energy does not disappear. Your coffee does not get cold because the energy just got zipped up into nothing. It spread out. It went into the air. It went into the table it was sitting on. And you pick up a coffee cup, it's hot underneath. So that heat energy is kind of spreading. It goes to other places, flows. So the laws here are about conservation. There is no getting rid of anything, magically appearing. It is always conserved, but it can be transformed. Now that you're familiar with the laws of conservation, let's try an example. I want you to read through this problem and then tell me what you think. You can never violate the laws of conservation. So this does not violate the law of conservation of energy. The coffee cup just got cold because it went into the desk underneath it, like we were talking about. It went out into the air. You've seen steam coming off from coffee. So the heat is just spreading out. It's not being, disappearing into thin air. We're going to talk a little bit more about atoms now, and you should know that atoms are absolutely the smallest building block of life. They make up all things. The current periodic table actually has all 118 elements. So there are 118 different kinds of atoms in the world. Only 91 of those atoms actually exist on their own, like naturally. Others have been artificially produced in laboratories. We call those synthetic elements. Atoms are made of protons, neutrons, and electrons. Protons and neutrons, of course, are in the nucleus, which is in the center. You should know that that is a very, very small volume, but almost all of the mass, like arguably 100% of the mass. The electron's mass is so negligible, losing the mass of one electron would be the equivalent of pulling one hair off of your head. It's not going to change your actual overall mass in any measurable way. So all the mass of the atom is really packed into the nucleus with the protons and neutrons, which by the way are of equal mass. And then the electrons, even though they're so small, they're going to create most of the volume of the atom. The catch is that they don't like each other. They repel each other. So you're going to get a lot of empty space in between. So kind of a tricky test question I've seen before is, what is an atom mostly made of? And if you're talking volume, the answer is mostly empty space. The different elements are actually named after how many protons, neutrons, electrons that they have. The main thing that drives their name is the number of protons that they have. But we can also have variations of those atoms. We call those ions and isotopes. Maybe you've heard of that before. So when we look at these, we say it's lithium. We can tell how many protons, neutrons, and electrons we should have for each of these things. So essentially what the periodic table does is it takes that label for calling lithium the thing that has 6 protons and puts it in a pattern with other atoms, so we can represent all the different types of elements that we have. And then this is all organized by something called the atomic number. And you should know the atomic number is the number of protons that they have. This may actually be new vocabulary, so make sure you write that down. The atomic number is the number of protons that they have. And the atomic number can always be found on the top of the elements block on the periodic table. Last, we're going to talk about physical and chemical properties and changes. So we'll start with physical properties. So physical properties can be observed without changing the identity of the substance. This means that you can simply look at it and see it, or you can put it on some kind of measurement tool and take that measurement. Most people are used to thinking of physical properties as simply qualitative, I do want to point out that you need to get used to thinking of quantitative things as well. You could put something on a scale and say how much the mass is, and that would be a good physical property. You don't have to change the identity in order to put it on a scale. But it does also include things like color and shape, texture. If you didn't have to change the substance to observe physical properties, you shouldn't have to change the substance in order to determine its physical changes, or to see physical changes, I should say. So when you have a physical change, you're just changing the physical form. So the major examples that I really want you to know, any kind of phase change is a physical change. This includes not only melting and freezing, but also boiling, like sublimation, all of it. Any phase change is a physical change. H2O is always H2O, regardless of whether it's an ice cube, liquid drinking water, or a water vapor, steam. It is all H2O. Some other physical changes might be like grinding, like if you put your pencil in a pencil sharpener, it's still made of graphite and wood. Or dissolving, like you take your sugar, put it into a glass of iced tea, make some sweet tea, that you still could evaporate out the water. You could separate the tea particles, you could have your sugar all separated. So it's not combining into any kind of new substance. In order to identify a chemical property, you do have to actually change the substance. So a couple of examples would be how reactive something is. Like for example, there's a particular group on the periodic table that is extremely reactive with water, meaning you mix it with water and you're going to basically get an explosion. Some substances are not that reactive with water. There are plenty of things you can put in water that don't explode. So that degree of reactivity would be an example of a chemical property, but that's not something you could observe unless you actually mixed with water in order to see what would happen. Flammability is the same thing. How do you know if something's tending to catch on fire or not? You would have to actually catch it on fire, and once it's going to catch on fire, it's going to change into a different form, different chemical. So flammability and reactivity are good examples of chemical properties. You must change the substance in order to observe a chemical property. Chemical changes involve a completely new substance being born, or I shouldn't say born, being formed. So forms one or more new substances. It's going to involve rearrangement of bonds. So you're going to see usually a type of chemical reaction where you have reactants forming products. This example of the acid reacting with the egg is an example I use sometimes for lab safety. If you put acid on an egg, it actually looks like it's cooked, and that's the same thing that would happen if you got acid in your eyeball. It would actually solidify the liquid inside of your eye and cause you to go blind. So that is a chemical reaction. Anything that completely changes into a new substance, such as with cooking, that would be a chemical change. The tricky part about chemical changes is it's hard to tell if you have a new substance. How can you tell if there are bonds formed and bonds broken when that's at such a small molecular level? So we've got to look for things that are actually visible to our eyes. So that would be things like flames, because burning is always a chemical change. If you see a gas being given off, like bubbling, a lot of times bubbling, like with Alka-Seltzer, could be considered a chemical change. Just be careful that it's not just simply boiling, because phase changes, as we talked about, are physical changes. And then also, if something has a completely different physical property, like if the color completely changes, well, then that's probably something different. So you're going to look for things like this in labs so that you know that there has been a chemical change. We're going to end with a couple of examples. For this one, what kind of change do you think evaporation is? What kind of change do you think breaking is? What kind of change would boiling be? What kind of change would rusting be? And finally, what kind of change would burning be? Alright guys, that's the end of Note C for Unit 1. We have one more set of notes left for Unit 1 in Notes D. We're going to talk about different phases of matter and how temperature plays a big role.